There is a button here.
Use this
No,
one.
that's okay.
Okay. Now?
You see what my problem?
No.
I try to
There
push
is
the same button as she does, and for me it doesn't work. So that's one of the many mysteries in life, and this is one. Just you see, somebody was asking me 5 minutes ago what is my background to talk about these kind of things, and I can tell you that I started my career in crystallography. And you may know that crystallography is the most boring section of physics, and because really you just run through programs, computing, and you find the position of the atoms. It's extremely boring. So I moved to something that I think I was not a very good crystallographer, and so I moved to another field. I'm not very good at this either, but at least it's much more fun for me. So I try to tell you a few things about this idea that we can perhaps model the world, the economy, the ecosystem, and mineral, or generally speaking, natural resources. So we have been seeing things in this field today, several presentations discussing the same subject from different viewpoints, and I'd say very interesting presentations, all of them necessarily. These presentations had to be partial because it's so much, you had noticed that, so much material to cover, resources, energy, ecosystem, feedbacks, the system, everything. So what are we doing essentially? I took this image from a science fiction story. You know the story of Asimov, the galactic trilogy. This is supposed to be Trantor, the capital of the Galactic Empire. It's supposed to be written in the 60s. Was supposed to be a planet completely covered with concrete buildings. And eventually, I think we are going somehow in that direction. I don't think we will arrive exactly to become the capital of the Galactic Empire. But we are doing things. Of course, you have seen there's something wrong here, but anyway, you can see this with the amount of minerals that we are extracting, although the industry prefer the term produced. If you speak with anyone in the mining industry, we say we produce mineral. It is a sort of, it makes a difference, because if you say we extract, we say something that was there already. If you say we produce, you create it. And there is a difference, but we are extracting, I prefer this term, huge amounts of materials, and as we saw it already, increasing the amounts so far. We have been going this direction. This is especially impressive. Sorry, I don't know what happens here, but you see, this is the same thing as the button that I try to push, and maybe you can fix this. Can you fix this? No, it doesn't matter. Anyway, this is cement, concrete. See how fast it goes? It's fantastic. If you model this in terms of an exponential growth, you can calculate that before the end of the century, we get something like Trantor. At least Europe will be covered with concrete all over. And so I think, honestly, that there is some problem with this idea of growth, because you see the problem with this. By the way, do you know what are the countries which produce the most concrete per person? One is China, the other is Italy. Some reason Italy. I don't know why, but that's it's because we have a five-star movement. We have Berlusconi. We produce a lot of concrete. There's some. There are mysterious things in the universe. We can model the system as much as we want, but this we will never understand. So the point I want to make, anyway, that this kind of growth has to stop at some moment, evidently. It's impossible. It cannot keep going like this. And you heard, especially about oil. Let me speak a little bit about oil, because it's a subject that is very basic, very important. It's a paradigm of the whole story of extraction or production. So you know the story of peak oil. Of course, you heard it, and it's interesting to say right now, because it's March March 1998, exactly 20 years ago, Colin Campbell and Jean Laherrère, they published this, I'll say, the seminal or paper or milestone paper, which said, okay, we are going to have problems. They revived an old model which had been proposed in 1956 by someone named Hubbard, Marion King Hubbard, and they proposed, well, okay, what was the idea? Notice that they didn't say we are going to run out of oil. Correctly, they said we are running out of cheap oil, which is very different, and they had a few things very clear, and they said, okay, the problem is going to appear, they said, around 2010, and we are going to see increasing prices and supply problems. So 20 years later, how did we fare? Well, yes and no, let's say. This was the prediction in 2008, 10 years ago. So this is gas, this is oil. So we should have peaked around 2010, more or less. We haven't, because something happened that changed things, which is shale oil, or tight oil, if you prefer, a large financial effort that went through extracting or producing, as you like, this kind of oil, which changed things enough that although the prediction, if you refer the prediction to what we call conventional oil or regular oil, which is the kind of oil that you dig a hole in the ground and then you extract liquid oil, then the prediction was not bad. It's reasonably good, but the industry moved into different forms of oil, especially shale oil in the US, which allowed production to keep going nearly linearly. So in a way it was a good prediction, in a way it was a bad prediction. You all know that all models are wrong. But you also know, and this is very difficult to explain to people, politicians in particular, all models can be useful if you know what you're doing. So the model, the 1998 model, was a useful model, I think, because it told you, look, you're going to have problems, especially about prices. Because unfortunately, I have some problem here. You can model. You can model whatever. I ask you a fit of fantasy now. I'm sorry, because there's something badly wrong here. Well, maybe I show you this. Maybe I show you this because I'm missing two slides. Let me tell you the slides rather than showing you a blank form. Let me summarize what I wanted to tell you. That peak oil was a decently good model, as it was proposed in 1998. As a model, it didn't fare so bad. It predicted the increases in prices. Then, of course, the prices went up and down. Right now are about $65 per barrel if you follow the oil market, which is by no means a low price, but it is low in comparison with the 100 and 120 it was a few years ago. So it depends how you see things. But unfortunately, the slide that I want to show you here, it was the most interesting one. I think it's, you can imagine it, I'm sorry. No, seriously, I went to make a search. No, okay, yeah, I'm sorry, it's my fault probably. I used.
Are you using a Mac or a PC?
No, I was using a Linux computer, so probably that's the reason. Anyway, this. Okay, yeah, good point. Yeah, there is such a thing. This is what is a new technology, right? It's a energy-saving technology developed in China. Anyway, this is time. Correct. How? Great. It's a post-peak. Okay, peak oil at the maximum around 2005. Number of web searches. This is extremely interesting, I think, because it has to do with the way we relate with models. Because I don't think it is because of Mr. Trump abolished the idea, but there is sort of meme fatigue. I use this term. You know what is a meme? Yeah. So peak oil is a meme, and it aroused a lot of interest up to a certain point. Then it went down, and this is so typical of many of these ideas which have to do with the future. If you go looking at the limits to growth as a behavior which goes like this. Limits to growth, the 1972 book, went up like this and then down at the maximum around something like this. So there is a depletion in some way of the meme. Despite the fact this could have been a good model or a bad model, but there is no more interest in it. And why is that? For some reason, we have difficulties in getting these models in our mind, and they sort of fade away from our consciousness. I'm afraid, actually, that this may happen also for climate science. Because if you look at this, climate science has had, if you look, global warming goes like this. So maximum at some moment. And people get used to global warming. Nothing horrible happens today. People will tell you, what is global warming? You see, it's snowing, it's a stupid idea. And eventually they lose interest in ideas. But anyway, when we deal with models, we make assumptions about the human mind, how the human mind reacts to models. And the human mind of the people who take decisions, it's different than the mind of physicists. Very different. So what is inside here? It's, it's something that needs to be studied, by all means. Don't you think so? What Mr. Trump said, we have coal for 1,000 years. Was he right? What did he base his statement on? And there is reason. Mr. Trump, in my opinion, is far from being stupid, by all means. The whole debate, if you go out of this room, we are all modelers here, most of us at least, people who know dynamic systems, they use sophisticated models, but the whole issue, the whole debate, when you happen to work with crude oil, people will ask you, Professor Bardi, do we still have oil? And then it's binary, yes or no, 0, 1. You said 1, no problem. You say 0, disaster. But it's not like this. But if you show this, and this is the standard image that you will get from the oil industry, the fossil fuel industry, they say, okay, we have lifetimes of fossil fuel resources, and we have 20 years of oil, no, probably 40 years of oil, 50 of natural gas, so hundreds of years of coal. So what is the problem? Is there a problem? The problem is not in this data, which are correct. The problem is inside here. The people are not used to reason in dynamic terms, but that's a lost task with politicians. But let me show you something. For instance, this comes from Bloomberg. This is not exactly a den of catastrophists. And what's happening here? If we have 40 years of oil, crude oil, where is it? Why can't we discover it? Careful, this is regular oil. Regular oil, you have to discover it. Tight oil, you know where it is, you have to extract it. It's a different story, but in terms of crude oil, which is the cheapest form, it is running down, evidently, because we are not discovering enough of it to replenish the resources we use now for production. It's, see, theoretically we have 40 years, but we cannot keep producing it. So essentially, looking at this, you see that the peak oil idea was correct, essentially, because the problem is that we are producing now about 28 billion barrels per year. So we have been discovering less than we produce for the past 20 years or so. And this is some sort of a problem, but we have to understand it, which we can. If you are a physicist, if you are a scientist, if you know anything about system dynamics, but you have to go away from this simplified version, which is the one which is typical of when you discuss with someone who is not a physicist. Well, they said, do we have it? We don't. Is it cake? Do we still have cake? And you have to tell them, this is the culinary session of the no, don't worry. That there is a difference. Normally you might start with the cherry, then you eat the cream, then the cake itself, and then if you're really hungry, you will eat the paper paper dish. And the situation is more like this. Tiffany's jewelry fallacy, which I use this term, trying to explain to politicians. I've developed all sorts of metaphors, and none works, but just for fun. So if I were to tell you, or the financial advisor of the lady here say, you are rich. Why? Look how much gold is there. You are rich, but you have a little problem. Problem is how to get it. And it takes some work. Either you make money and you buy it, or you break the glass and you get it, but it's complicated and difficult. So the basic point, though we still have some problems here, but the basic point is that mining requires energy. And the whole point, which we have seen in several presentations already, that in order to mine, you need to spend energy, and if you mine some mineral which produce energy, then you have the energy return on energy invested, the concept of EROI, which is becoming more and more fundamental here. And this gave rise to a new paradigm, which is a series of books and studies which use this concept to, let's say, we are going with these books. This is one I wrote. There is my name here, but it's disappeared. And once you start seeing the situation in these terms, like in the talk that Fatma gave, you see there is this problem. You have to expend more and more energy to extract, to keep going, to keep expanding, to keep moving. And the problem is all here. You see, this is, fortunately, it's a good slide. You see, this is, here you have prices. But as a first approximation, the price of extraction is proportional to the energy you need to extract. So these are your reserves of oil, but they are not all the same. Oil becomes more expensive as you go to the so-called unconventional, non-conventional oil. So the energy yield of these new resources, these wonders of technology, or shale, well, here there is no shale oil, but anyway, it's somewhere here, shale oil, and you had to spend more energy, which means lower net energy, lower energy return, which is typical of all sorts of minerals, like gold, for instance. You go from this, you almost can see the gold nugget was easy once. You could just go pick it up, 100% gold, and now you extract from minerals which, you don't even see the gold here. You need a microscope to see the gold. And this is the same image that Fatma showed. You see, we go in general to lower ore grades, and we go down, we spend more to get the same, and even more to get more. So this is a trend.
We are spending less, actually.
It depends. But I have a point that I want to show you. I'm working on this right now. Whether the lower energy returns are already affecting the economy, because you see this is the EROI for oil in the US. It's gone down, halved in the 1970s. So this is a slide which was already shown yesterday, I think. All the numbers here are wrong, but don't worry about that. Qualitatively, it is good. You see, the problem with EROI is the same that we have with communism. Communism, in principle, is a very good idea. Then we try to put it into practice, it becomes a bit more iffy. So the same is for EROI, because calculating the values is very difficult and you have a large spread. But anyway, it is clear that we are going down, and at this point, you had this big change in the social distribution of wealth in the United States. Up to 1970, peak oil in the United States, you had more equality growing, and then from then on you changed completely the behavior, and now United States is a very unequal society. These values of the Gini coefficient are same as middle-age Europe. In Europe is a little bit better in terms of equality, but we are growing in that direction too. And my impression, while trying to model it with my coworkers, that the higher cost that you have to keep producing, like when Mr. Trump say we are gaining energy dominance because we produce more. And we produce more, we spend more to produce more. Where does the money come from? From the poor. And the poor become poorer, and that's the result. I think this is one consequence of the story, but this is just an idea that I ask your opinion if you have a moment later, because I'm not sure, but I think there is something in here. But this is not a model. It's just an intuition, an idea. We have this. Maybe this is the consequence. So the question is, how do we really model these things? And, okay, you get there. Lotka-Volterra. Since I am Italian, I put the image of Volterra. But of course, it was a shared work by Mr. Lotka and Mr. Volterra back in 1920 something. Okay, so this is, I think, a very good model, because it's known to be a toy model for biologists, and in this sense it never works. But it's a very sophisticated model. Actually, you can do a lot of things, and I have to apologize to the quality of these images. I'm sorry about that. There is some problem here, but anyway, what I wanted to tell you was, so you can see something yet. This is the Limits to Grow, the first edition of the Limits to Grow, 1972, which was based basically on the same concept. The coupled feedbacks of predator and prey of the Lotka-Volterra model, but it was more complicated, not so complicated compared to our models, the models we have today, but it was very complicated. But if you look at the sub-units of the model, you see that they are versions of the same idea. You have some capital which grows on some resources through a feedback relation, which is the basis of the Lotka-Volterra model. And as you know, okay, never mind. You can still see it. Takes a little fantasy, right, to know this famous. You have this bell-shaped curves, which is a typical output of these models. When Hubbard developed his peak oil idea, he just assumed that you had this bell-shaped curve, but it is actually the result of this kind of dynamic modeling. But of course, today we do much better than this, and what we do, I am involved in this project, which is in a way a re-edition, or we're doing again a world model. For a certain period, world modeling was not anymore popular. It was supposed to be all wrong, useless. This is the tough life for the modelist. But now it came back in fashion, and the European Union financed a model which is very similar, more complex, more detailed, but very similar to the 1972 so despised model. I don't think they knew what they were doing when they financed us, but anyway, never mind. And it gives you essentially the same results. We are careful, we don't say it so explicitly, but this model predicts collapse of our civilization, but we will go to that. And now let me, in time, let me, how much time do I still have? 20 minutes. We have time. Okay, anyway, let me extract from the model, the very simple model, mind-sized, as Fatma said, right? Mind-sized model, try to, I think still it is much oversized for a politician's mind, but anyway, you know, and Jacques mentioned the EROI and the Lotka-Volterra model, just the first talk on Monday, and actually they are the same thing, because you can use the Lotka-Volterra equation explicit the EROI. You can embed the net energy return in the equations and calculate it, and then you have something like this in a very simplified model, but you can see that production goes to a peak if the resource is non-renewable, and you go down with the EROI, and you can go negative with net energy. You can still keep producing because you don't know exactly when you produce, you don't know exactly what is the return. So you keep producing even with a negative net energy with an EROI lower than 1. And eventually the whole thing will collapse. Notice that the net energy curve follows rather closely the production curve. And of course, Fatma did very good work adding prices to this model. This is a very simplified model which assumes that prices remain more or less constant. If you add prices, then you can stretch the curve and you get resources from other sectors of the economy, and you keep growing even though the problem with EROI remains the same. That's a physical characteristic. You cannot change it anymore, but you can still extract even with very low EROI. If you get money, if you get resources from another sector, you keep going. But in some cases, and that's a point that maybe you were missing in your talk, and if you allow me a suggestion to convince people that the model you use is good, you can show some historical cases. And we found in our research that fisheries provide an excellent test bed for this model, work beautifully. For instance, for whale oil, whaling, you can read it more or less. You have these two beautiful curves modeled with a simplified model. There's no prices here. Actually, we can see the whole cycle here. That's a big advantage. We are not extrapolating in the future. This is the past. The cycle of whaling, the American actually whaling, the same as Moby Dick. You know Moby Dick, there she blows, go ahead, Captain Ahab, go, and things like that. But not just this one. We found that the fishing industry offers a lot of examples of curves, beautiful, bell-shaped curves, so that somehow myself and my co-workers become experts in fisheries, which we didn't expect that, but we arrived to a very simple conclusion. And you can see that eventually it all comes back to a very simple conclusion. Because you have to know this, you start working in fisheries, it's fascinating, incredible, and the condition of the oceans is a disaster. It's unbelievable how humans could rip off the ocean, destroy everything, kill everything. The oceans now are basically empty of fish because overexploitation, a total disaster. I don't know how it could be done, but it was done. It is being done because politically it's impossible to stop it, but that's another story. Just to keep going a little more, so many things in this area, just show you that if we go to a little more, in some case, you can complexify these models and enjoy life. You play with stocks and flows, and this is the Seneca effect. Why the Seneca effect? Because the Roman philosopher Seneca, back in the 1st century of our era, he said something. So he noticed something that everybody knows, but in everything there is somebody who noticed it first. And he said that it is a strange thing that things grow slowly, but decline rapidly. Somebody had to say it first. Ruin is rapid. Growth, fortune is slow, but ruin is rapid. He says something like that. And so I use this name to a model which is good for many things. We use it in fisheries. Fisheries. It's a fascinating field. You see, this is the Caspian sturgeon, caviar. Do you like caviar? It's very good, caviar. But you cannot have anymore the real caviar. You have farmed caviar with the sturgeon fed with all sort of awful stuff. It's not very healthy anymore. But anyway, you see, it happens, and there is a whole fauna of. Once you start playing with these models, you can. I teach it to my students with the example of Amélie the amoeba grows in a petri dish, and can have different. If Solo had been an amoeba, he would say we keep growing forever, but in the petri dish. But that is not possible. Malthus had the idea that you have to stop at some moment. Hubbard had the idea of the symmetric curve. Seneca never thought in terms of Cartesian diagrams, but anyway, if it is a modern idea, and then you have also the Hokusai curve, which the system does not just decline rapidly, but it actively chases you to destroy you. It can happen. That I don't have a mathematical model for this, but maybe one day. Okay, so you see, but there is a huge amount of things, a huge number of things that could be said about this. It's very fascinating. But let me go back. I have 10 minutes to say how this can be used to model the transition, which has already been seen in other presentations. Let me show you our interpretation, me and my co-workers. You see, the problem is this, and I think it gives you the idea of what we're trying to do. It's impressive, this, right? We had to grow this to the point that we overcome this, and it's a tall order, as you say. No, we have to do it by 2050. And we are paid by the European Union to find ways to do it before 2050. This is not impossible, though, because we can use the Seneca effect. Seneca cliff can help us. These are some calculations we made, and you see, this of the violet is the fossil fuels, and you see the Seneca curve going down and disappeared by around, could do it. This is based on physics. It's not just what we wish it could happen, but something that could happen, actually, if we are able to divert some energy from fossil fuels to renewables. Because right now, the situation where it is now, it's impossible. As correctly, people say we need coal to make solar plants. So we need to use fossil fuels now. Then they will be self-renewing themselves, but it takes some time. And we can calculate the physical parameters needed here to do this. It's all based on physics, not economics. That maybe one day we will be able to do this, but surprisingly, it turns out that it is possible. We can still invest enough energy. We can divert about 10% of the energy we produce in order to make the new infrastructure that will create a more sustainable, hopefully, world. And this is something that we call the sour strategy, which is based on the idea that's very old, very ancient. If you are a farmer, you cannot eat your whole harvest, you had to save a little bit of the harvest in order to seed the new harvest. This is what we should do. And our farmer ancestors, they knew how much seed they had to save, because if they made a mistake in that, you won't be here, evidently. And this is something that we can calculate. By the way, this is totally impossible to explain to a politician, but never mind that. We try to do, you see, developed metaphors, but I lead to something even simpler, but never mind that. Problem is that it comes out that we need to invest at least 10 times more than what we are investing now if we want to go through this curve. If we want to go through a world fully based on renewable by 2050, more or less, then we need to invest much, much more than we're investing now. And the problem is that we are not. As a first approximation, again, the amount of money we spend is proportional to the energy invested. We made more detailed calculations, and so this is a big, this is a civilization failure, as you can see. If we keep going like this, if we don't increase this amount, and this is politically impossible to increase it right now, then we're not making it. This we will get, not a problem, but this will not go up like this. It will go like this and fall down and stabilize somewhere. We haven't done the calculations because it is politically incorrect. But the situation is bad because politicians don't understand what the problem is. So politicians, most of the public, think that we can have what we need just because we want it, like the coyote of the cartoons walks on thin air until it discovers, oh, look, I am on top of a cliff, and then it falls. But so I think we're going to get something like this eventually. So people say that I am a catastrophist. Yeah, am I? Maybe. No, I'm not really a catastrophist. I think someone will survive. Seriously, I think is the definition. But seriously, this is nothing new, actually. The Seneca cliff, the Seneca is normal. It's a normal occurrence of the universe. So you see, we have this figure for the Black Death in Middle Ages in Europe. You see the Seneca cliff? Wow, that was tough. It was a Seneca cliff. It's normal, it happens. I think it will happen to us because we've done too much. We are overexploiting our resources, so we are going to, hopefully not so harsh as this one, or something like this. And that was not the end of the world. Actually, if you read what people were thinking in this period, they were very pessimistic. Everything is falling apart. But no, after, you know what happened here, at this point here? Columbus. So I've always wondered why it was that Europe, at some point in 15th century, you had this small peninsula on the west of Eurasia, not important, small, not so many people. Then they became the conquerors of the world. I think it was a rebound of the great. No, just 1 second. A rebound. 1 second. I show you on the next slide. A rebound of the Black Death, which freed a lot of resources and allowed Europeans to engage into exploration of the world. And incidentally, the Chinese were doing the same exactly in that period, having been affected by the Black Death as well. It spread all over Eurasia and affected China too. And so during the rebound phase, they started with oceanic exploration fleets. So I think it is not impossible to think that this future may not be collapse after all. We will have some kind of decline, but then we rebound. I was discussing with Robert about space mining. Space mining is a typical science fiction idea, and it will never work. Not in these terms, of course. There is no way that you can take minerals from space and bringing them back to Earth. It's too expensive. Makes no sense. Maybe, and there is no gallium on asteroids, so you cannot solve that problem. But there is a big rebound of the idea of space mining, not so much for bringing things to Earth, but self-sustain structures in space, which is, I think, is interesting. We are not going to space. Humans will not explore space because we discovered that it is an environment in which humans cannot survive. But our robotic children will probably do something like this, I think. So you see, it's very complicated. I think the whole thing I can say eventually is to do this, because, as I said at the beginning, all the models are wrong. And don't trust the models, don't trust the modelers, don't trust the physicists, and not even the politicians, but install renewable energy plants, which I think is a good idea. Thank you.
Questions? Okay. José?
What are the renewable energy?
I'm sorry?
What are the renewable energies?
These renewable energies are everything you can use. No, I don't have them here, but you said that renewables are not renewables. No, they are, because photovoltaic panels don't use gallium, don't use indium. They use just silicon and aluminum and tiny amounts of boron and nitrogen, a little more. So you will never run out of aluminum and silicon. There is plenty of silicon and aluminum in the Earth's crust. So that's not a problem. They are renewable.
They're not, because you have to build the ingot first, and when you build the ingot, you're fighting delta G0 all the time.
Nothing wrong with ingots. I don't see anything wrong with ingots. If you have energy,
if you have energy to
but
build
the energy is
energy.
produced by the renewable plant.
It doesn't exist.
It is. What do you build for a renewable energy plant? You build it to produce energy. Then you use this energy to produce ingots if you want.
It's not the way it's done now. It's done on
It is not
carbon,
done now, but please think
coal.
about the future. You said in your presentation you were thinking about the future. Don't lock yourself into the present. Think of the future. You have energy. A renewable energy plant is there to produce energy, and it does. There is no doubt about that. You don't need coal to make a silicon.
It depends on the EROI.
No, you use electric power from an energy for a renewable energy plant, and you build as many silicon ingots you need. There is no limitation to that.
Okay. I don't believe a word of that.
You don't believe, but think about that, because you have it completely wrong. I'm sorry. You didn't understand what is the energy return on energy invested. You need to make up your mind to understand these things. It's basic thermodynamics. You know a lot about electronics, but you don't know enough about thermodynamics.
I just want to mention one source of renewable energy that nobody's actually discussed recently. It was very popular 20 years ago or so. It's one of those disappearing peaks. But I'm talking about solar satellites. And solar satellites could very well be the answer to some of these problems. They were technically feasible then, just not economic, but that's a different
No, that's a great idea, actually. It needs a big investment, but there will be a conference in Italy, if you want to come, about space mining in Milano in June. And one of the ideas is space power satellites, which can only be built with minerals taken from space. But for a space power satellite, you only need silicon, aluminum, and a little more. And so you have plenty of silicon and aluminum in space. You go to the moon, you find as much aluminum as you want, too much. And it is a way, indirect way, to use space resources to to bring other kinds of resources, in this case energy, to Earth. I think it is still a little bit far away in time, but it is. It was promising in the 70s, yes, but then.
Then oil didn't get expensive.
Yeah, that's right.
They've been
Yeah.
scheduling $400 a barrel.
That's right, that's right. Then everybody started thinking oil is abundant, it will never run out, just like now.
We go through cycles.
We go, yeah, exactly. We go like this.
No, I have the mic, so I can talk. Ugo,
Yes,
Here.
who are you?
here.
Who's speaking? Okay, sorry.
Yeah, just in the previous sessions that we had here, we addressed a number of questions that are implicit in what you say. For example, how much with the present technology that we have, or that we don't have, for storage, for example, storage of energy, how much intermittent or variable power you can put in a grid and keeping the stability. And so there was several contribution in that, and the conclusion was that it's difficult to go beyond 35 or 40%
Yes.
of renewable. I mean, of these new renewable.
Yes.
So
for
that's
the-
one point you have to address, because that's a lot, 35 or 40%, but then you still miss 60. So what do you do with the 60 if you want to get rid of the fossil fuels? That's one point. The second point was about EROI, and then I showed the slide, but it was very, very, very quickly and not convincing. But Weisbach and other people also have calculated the EROI of the various sources, and of course there are large uncertainties, but definitely it points that if you take into account the buffering, I mean, that you have, to compensate for the fluctuation, the EROI is between 5 and 10. And so that raises a question. It doesn't mean that you cannot do it and you cannot live with that, but that you have to address a few questions to see.
Absolutely, Jacques. It's
that's
perfectly correct. This is a very coarse modeling. It assumes that you can replace 1 kilowatt of power of fossil fuels with a kilowatt power of renewable energy, taking into taking into account, but it takes into account reasonable cost for storage. That is in the model, but not in details, because the model doesn't go into such a detail as to say how can we keep the grid stable with a system 100% based on renewables, which is correctly a problem. And there are many. The point is that what are we doing here? We're making models to see what is possible, what is not possible. Then we go into details. If we fall into the trap, the negative trap of thinking that renewable will never be possible, then we don't even make models. We say, well, okay, we're going to collapse in 2000 and go back to agriculture, which may happen. I mean, it's not impossible. We are doing this. You see, this is an ethical model. We try to see if it is possible to keep 9 billion people alive throughout the 21st century. It is possible. It would be possible if we were willing to make sacrifices, which means also accepting that the grid will not be available 100% of the time, because you have to adapt not just the supply, but also the demand. Because you say, it's like I make the example with politicians, I'm sorry, of cherries. You want cherries. In today, you won't have cherries, but that doesn't mean the cherries don't exist. You have to adapt the demand to the supply. If the supply is variable, which will be probably if we have to move to renewables, then the demand will need to adapt to the supply, probably by a pricing mechanism, maybe. But again, we are moving to a different world in which we will ask different questions. If you ask the question, can we keep the world exactly as it is by renewable energy? The answer is no, there is no problem. But if you ask, what kind of world can I have with an abundant supply of renewable energy, then it's a completely different kind of questions. Incidentally, about the paper that you cited, it's a good paper, but it's a little bit obsolete. Right now, we have much better assessments of the EROI of silicon solar cells, and it is close to between 10 and 12. And which is reasonably good. It's still not the same as oil, but I think we can build up a civilization on a source which has an EROI of 10. It is perfectly possible. Some people, you see this, there is this game that some people play with this image. Some people put the point here, minimum needed for civilization, which is, in my opinion, it's completely stupid. What the hell do you know what is the minimum needed for civilization? What kind of civilization? If you want to have a SUV, you want to take a plane to Hawaii, yeah, probably you need oil with about 20 of EROI, but if you...
All right. Next question actually was back on the colorful graph. So you were there. If you could go back to the beautiful colors of the future graph.
Which one?
The beautiful colors of the future graph.
Well,
oh, there it is.
yeah.
There it is. Yeah.
Oh, you mean this beautiful black?
Well, yeah, that's pretty black. All right. So the in the past, the purple, people have invested real money, and they built real things, and they got real returns on that. Nobody is more wealthy than oil companies and gas companies. Okay. So right now, if I have some real money and I want to invest in something, you gave a great advice about what we must invest in. We must invest in something in the future. And you said invest in renewable research or research for renewables. I'm trying to advise somebody on how to invest money. Invest in renewables or invest in using a lot less purple energy. Because I know that for sure. Yeah. Well, if I invested in getting down to 500 and having a good life.
That you cannot survive with 500. 2,000 watts per person.
Who's trying? Who in this world is, who in this room is trying that project?
If I were a Chinese peasant, I could probably survive on 500 watts per person, but this number right now in Europe we are about 5,000. So it is in the
right.
In the,
but
in
if
the
I was
model.
going to invest in research, knowing something about the future, investing in research to find out how to have a good life on less energy might not be a bad idea.
It's not a bad idea.
Don't want to know though.
I agree with you.
Okay.
Only thing I say that that sometimes a fraction of what we call the environmental movement, they tend to overemphasize, in my modest opinion, the question of energy efficiency and energy saving, sometimes forgetting that you can save something only if you can produce it, if you have it. So I think we will be much more efficient in the future. There is no doubt about that. But we need a minimum of energy. This is real a minimum. We think you can go down a little bit, but you know the problem when you go down, what happens? It's not that everybody goes down the same amount. What happens when you reduce net energy, the available energy? You get something like this. The poor get very poor, and the rich keep their standard of life. And so I think this is a big limit to this idea of reducing the consumption of energy. At least I think.
The two last questions, Antoine and Klaus, and we will ask them together and a short answer.
Okay, so you showed that the Seneca cliff may happen to a population that are not aware of the Seneca effect. How do you have any ideas what would happen to population that are well aware of the Seneca cliff and how this would affect the Seneca effect. For example, if you would tell every single fish that they would undergo the Seneca cliff, could the Seneca effect be changed by this?
This is a very interesting question. You see, well, when you deal with these kind of things, you see, this is the Caspian sturgeon, and you have a very nice Seneca cliff here. Now, good question. Were people aware of what they were doing or not? I think not, or yes. Something that some people involved with psychology or sociology should study. Because what they have been doing here, they destroyed the resources which made them live. So why did they do it? Were they completely ignorant of what they were doing? Or yet they were saying, if I don't kill sturgeons, my neighbor will kill them? Probably.
Coming back to the EROI for solar energy specifically, I actually am a little optimistic on that point. And the reason is that the underlying solar panel, the first electricity you make, may be useless because it's at the wrong time, but it's also extremely cheap. If you look at the lowest cost long-term contracts right now, they're between 2.5 and 3 cents a kilowatt hour. And and there is a big if here, if we manage to follow the learning curve for the next few doublings, we have 5 to 7 doublings left before we completely saturated the market. At that point, the prediction, because you every time drop to 80% or 85% of what you were before, is well below a cent. It's somewhere between 0.6 and 1 cent a kilowatt hour, depending on your exact assumptions. At that point, you can afford a really lousy EROI on the storage side, because your input energy was extremely cheap. So yes, you don't look good in the overall EROI over the system, but since your input was much cheaper than oil, you actually get away with it.
If you have a large input of that, you have to say what you do at night. Sure. You run batteries, you make synthetic fuels, you do all sorts of stuff. You will never be able to compensate with batteries for this kind of fluctuation.
Yeah.
Numbers, you look at the numbers. You lose a factor 3. But you have pump stations as well, for instance. Yeah. Okay. Put numbers. I mean, you have to put the numbers. There is a paper.
Ladies and gentlemen, thank you for
So
your
let's
attention.
continue the debate at the break. Thank you. So please be back at 4 p.m. here. Sure. Thank you.